so if you would turn to page 505, section 7.6 is similarity transformations. We've done these. When we did Unit 2, which was Chapter 9, but we did it second because I wanted to get all those, the motions in that we would use to show congruent parts and all that. We've done dilations. All right, so a lot of this is review. A little bit of it is different, but a lot of it should be review. So this will look kind of familiar to you. So we're going to identify a dilation and the scale factor and the center of dilation. Now, our book's not real good at this because all of the ones they give us on a coordinate plane, the origin is the center. So we're not really going to be doing that part, okay, because the origin is going to be the center. And then we're going to verify similarity after a dilation. So let's go back over some vocabulary. All right? A dilation is a transformation that enlarges or reduces the original figure proportionally. So a dilation produces a similar figure. So it's called a similarity transformation. If you remember, the other transformations we had were congruence transformations. Translations, reflections, rotations. The object did not change size. In a dilation, it does. It either gets bigger or it gets smaller. Okay? And dilations are performed with respect to a fixed point called the center of dilation. So if you remember, like right there is the center of dilation, and this blue one is our original figure. It's our pre-image. Okay? We would make little dotted lines that went through A, went through B, went through C. And then, and we'll worry about this again here in a minute, we would measure. And I think we talked about this more than we actually did this, because it's kind of hard to do. We'd measure. If the scale factor was 2, we'd find the distance from the origin or the center of dilation to A, double it, that's where J would go. Find the distance from there to B, double it, that's where K goes. Distance from there to C, double it, that's where L goes. And we would end up then with a figure that's twice as big as the one we started with. That's how we did that. Okay? That's still how it's done. The scale factor describes the extent of the dilation. So if the scale factor is 2, your new figure is twice as big as your original figure. The scale factor is 10, your new figure is 10 times bigger than the original figure. With fractions, it's a little more complicated, right? If the scale factor is 3/2, that's 1.5. The new figure is 1.5 times bigger than the original figure. You don't have to make them bigger. When they're bigger, they're called enlargements. You can make a reduction. If the scale factor was 1/2, we'd end up with a triangle in here that's half as big as the original figure. If it was 2/3, we'd wind up with a triangle that was 2/3 as big as the original figure. Okay? All that makes sense? All right. Now, they tell us here what we already know. K usually stands for scale factor. And remember with your scale factor, now that we're doing, starting with an original image and a new, it's not just one figure to another figure. The scale factor is the image over the pre-image, the new one over the old one. Okay? New one to old one is the way the scale factor works when we're talking about a dilation. And it always goes that way when we're talking about a dilation. Technically speaking, you can have a scale factor of 1. If I have a scale factor of 1, the new image sits right on top of the original image. It doesn't go anywhere, it doesn't do anything, it doesn't change size, nothing. So what good is a scale factor of 1 when you're trying to make a dilation? Not much, right? Okay? Now, an enlargement and a reduction are just unbelievably obvious. An enlargement is when the new figure is larger than the original. A reduction is when the new figure is smaller than the original. If the scale factor is greater than 1, it will be an enlargement. If the scale factor is between 0 and 1, it will be a reduction. Okay? It is technically possible to have a negative scale factor. What that does is it flips the new figure to the other side of the center of dilation. So if that's our center of dilation and that's our original figure, if the scale factor was negative, we'd make our little dotted lines this way, and our new figure would end up over here. It would look like a reflection. Not only would it change size, it would look like a reflection of the original one. So we're not going to deal with negative scale factors, but it is possible. That's what would happen. A dilation, and this is something direct from the standards that I can't find in our book, so I'm just going to put it in here. A dilation takes a line that is not passing through the center of dilation to a parallel line and leaves a line passing through the center of dilation unchanged. Now, that's the way the standard says it. It's not quite accurate, because look at this figure. If I call the small one figure A, the big one figure B, let's say A is our original one. Okay? So this line of figure A does not pass through the center of dilation. Its corresponding side for figure B is parallel to it. Okay? This side here, not through the center of dilation. The side that corresponds to it is parallel to it. Same thing happens there and there. It says if a line passes through the center, it's unchanged. The line itself, yes, unchanged. That's the line. But we're not really thinking in terms of lines, are we? Aren't we thinking in terms of line segments, because that's what the sides are? So the line itself, they're right, it is unchanged. But I think that's a little misleading, because we're talking about sides of a polygon. I'm not really thinking about lines, I'm thinking about segments. It's not true to say that the segment is unchanged, is it? Because the segment's there for the original figure, and then it's larger, it's longer in the new figure. Now, the one side's on top of the other side, so I get it. When they say line, they're right, it is unchanged. But the line segment is changed. It's going to get longer if the dilation is an enlargement. It would get smaller if the dilation was a reduction. Make sense? Okay. What say we do a few problems from your assignment? So turn to page 508. And we'll start with number 1. Determine whether the dilation from A to B is an enlargement or a reduction. Then find the scale factor of the dilation. So A is the blue figure, B is the green figure. So is that an enlargement or a reduction? It's an enlargement. Then they want us to find the scale factor. Now, we don't have to wonder whether or not the two triangles are similar. They are. If that's a dilation, which they tell us it is, they are similar. We don't have to wonder about it. In similar figures, all it takes to find the scale factor is one pair of corresponding sides where you know both lengths. So make it easy on yourself. Use those sides, because it's easy to get those lengths, isn't it? I don't have to use the distance formula. If I choose a different pair of corresponding sides, I've got to use the distance formula. Well, there's no need to. All right, now remember, it's image over pre-image. It's the new one over the old one. So count the spaces here. 1, 2, 3, 4, 5, 6, 7, 8 is the length of that side of the new figure. And what was the length of that corresponding side of the old one? 4. So the scale factor is 2. So every side of the new figure is twice as long as its corresponding side from the original figure. Does that make sense? Number 2. A is the blue one, B is the green one again. It's a reduction. Now we got to find the scale factor. So it's the new figure to the old figure. So find the length, and again, let's make it easier on ourselves. So if I count right here, what's the length of that side right there? 2. And then what's the length of this side right here that corresponds to it? So the scale factor is 1 to 2. So far, so good? Okay. Is it going to be easy to get the scale factor upside down? It is for me. I forget all the time. Is it new over old or old over new? It's new over old. Okay? New over old. So that's the new one. That's the old one. All right? Okay. Number 3. The dimensions of a regulation tennis court are 27 feet by 78 feet. The dimensions of a table tennis table, tennis table. Okay, that actually does make sense. Are 152.5 centimeters by 274 centimeters. Is a table tennis table a dilation of a tennis court? Tennis court, tennis. A court tennis court. That's only funny to me, isn't it? Okay. If so, what is the scale factor? All right, well, let's see. The shortest side of the table tennis table will correspond to the shortest side of the tennis court. The longest side of the table tennis table will correspond to the longest side of the tennis court. And I've already made a mistake. I shouldn't put equal there because I don't know if they're equal or not, do I? That's what I'm trying to find. Is are they equal? All right, well, there's a couple different ways we can go about this. Okay? Quite possibly the simplest way is to do cross products and see if they're equal. If you've got a fancy calculator, reducing those fractions isn't that big of a deal, but we don't all have fancy calculators, but we all have calculators that will do some multiplication. So if I multiply 152.5 times 78, I get that. Centimeter feet. And if I multiply 27 times 274, I get that in centimeter feet. Equal? Nah, they're not even all that close. So, not equal, not equal. Now, how do I want to answer this? Is a table tennis table a dilation of a tennis court? No, it is not a dilation because corresponding sides are not proportional. So the figures are not similar. And I do need to throw that last in because the whole reason it's not a dilation is because they're not similar. All right? The definition of dilation says you come up with a similar figure. Well, we didn't here. We shrunk the tennis court, and it did not come out the same when we made a table tennis table out of it. All right. We okay with 3? Number 4, we're going to verify that the dilation is a similarity transformation. So, verify. It is a similarity transformation. Those two figures, the blue one and the green one, are similar to each other. We just have to prove it. And we don't have to write a formal proof, but we have to show that they are. Okay? Now, one thing we could do is we could find, since we're on a coordinate plane, we could find the length of all 6 sides using the distance formula, and then show that corresponding sides are proportional. But since it's a triangle, we can save ourselves a little bit of work, because isn't angle DAE congruent to angle BAC? So we could try a side angle side similarity and not have to use the distance formula as many times. Okay? So I think that's the way to go on this. Is that the way? Yeah, that's what the book did too. All right, so we've got one pair of included angles congruent. So what I need to show now, you don't have to write this part down. I'm planning it out. I need to show that the length of AD to the length of AB, actually it should be the other way around. Well, I don't know which one's the original one, equals the length of AE to the length of AC. If I can do that, then I can use side angle side similarity. Make sense? Got to use the distance formula. So let's see. A is 0, 0. D is -2, -2. E is 2, -1. B is, let's see, -4, -4. And C is 4. That's not how you write it. 4, -2. Can you tell when I've labeled those vertices? Can you tell? Since you're starting at 0, 0, wouldn't -4, -4 be twice as far away as -2, -2? And wouldn't 4, -2 be twice as far away as 2, -1? Yeah. So it's gonna work out. So the length of AD is going to be, well, I've got to find them all. So the length of AD is the square root of -2 minus 0 quantity squared plus -2 minus 0 quantity squared. So that's a -2. When I square it, I get 4 there and there. So that's a square root of 8. The length of AB, that's not how you write a B. AB will be the square root of -4 minus 0 quantity squared plus -4 minus 0 quantity squared. Square the -4, square the -4, square root of 32. Ooh, I don't like radicals. That's going to be a problem. Okay, then let's find the length of AE. So that will be 2 minus 0 quantity squared plus -1. 2 minus 0 quantity squared plus -1 minus 0 quantity squared. Square the 2, get a 4. Square the 1, get a 1. Square 5. Length of AC, that'll be 4 minus 0 quantity squared plus -2 minus 0 quantity squared. 16 plus 4 square root of 20. All right. Now, I guess I'll just move sideways over here. Over here, the length of AD is square root of 8. The length of AB is the square root of 32. The length of AE, square root of 5. The length of AC, square root of 20. Oh, how do I know? How do I know? Well, do cross products. I don't know if you know this about radicals, but you can multiply two square roots together by keeping the square root sign and multiplying the radicand. The radicand is the number under the square root. So if I multiply square root of 8 times square root of 20, that's the square root of whatever 8 times 20 is. And if I multiply the square root of 32 times the square root of 5, that's the square root of whatever 32 times 5 is. So those better be equal. So I'll get my calculator back out. 8 times 20, so that's the square root of 160. 32 times 5, that's also the square root of 160. And we have verified it. Wow, hope I didn't give you 100 of those. The concept, fairly easy. Doing the distance formula a bunch of times, a little tedious, huh? Okay? And keeping the tedious in mind, just put a check mark by number 5, and let's say we did that. Let's talk about the theory of it. Does the theory of it work the same way? We've got angle J congruent to angle J in both of those angles. So then we would need to show that LJ and SJ make a ratio that's equal to KJ and RJ. So we'll do that. Side angle side. Okay? I'll save you a little work there. And me too. Okay? Now, something that we did back in chapter 9, it seems funny to be in chapter 7 and say back in chapter 9, was this. All right? So I took this out of chapter 9. When you're working on a coordinate plane and your center of dilation is the origin, to find the coordinates of your new image, take the original coordinates and multiply them by the scale factor. Okay? If I told you that 10 minutes ago, would we have to go through all that? We could verify it by using that. Because if we have 2, -2 here and multiply both coordinates by 2, don't we get that? If we have 2, -1 and multiply both coordinates by 2, don't we get that? And by the way, if we have 0, 0 and multiply both coordinates by 2, we get 0, 0. So all 3 vertices of the new figure were multiplied by 2 times the vertices of the old figure. So we could do it that way. I didn't even think of that till just now. We could do it that way. Okay? So let's do a couple of graphs. So this is not in your assignment from chapter 7, and I know you don't have a coordinate plane, so just draw you a real rough XY coordinate plane on your paper. It says graph the image of each polygon with the given vertices after a dilation centered at the origin with the given scale factor. So let's go ahead and graph W at 0, 0, X at 6, 6, 1, 2, 3, 4, 6, 1, 2, 3, 4, 6, and Y is at 6, 0. So there's Y. Okay? And we did these way back when. Since the scale factor is 1.5, I need to multiply the coordinates of each one of these by 1.5. To keep it simpler, instead of having to make up 3 new letters, we can just call our new coordinates or our new vertices W prime. Let me switch colors. W, that's a prime, X prime, and Y prime. And we get the new coordinates by multiplying them all by the scale factor. So, if I multiply 0 by 1.5, I still get 0. There and there, and in fact, there. What's 6 times 1.5? Oh, come on. 9. So when I multiply that 6 times 1.5, becomes a 9. That 6 times 1.5 becomes a 9. That 6 times 1.5 becomes a 9. So the graph of our new figure, the graph of our image, W prime is the same place as W. Y prime is right there. And X prime is right there. And they really do look like similar triangles, don't they? So that's not all that bad. We can do that. Let's try this one. In fact, before I graph anything, let's figure out what the new coordinates are going to be. For Q prime, R prime, S prime, and T prime. Since the scale factor is 1/2, multiply each coordinate by 1/2. What's negative 4 times 1/2? Negative 2. Positive 4 times 1/2? Positive 2. Go to R prime. Well, negative 4 times 1/2 is negative 2 again for both coordinates. For S prime, what are my new coordinates? 2, negative 2. And what are the coordinates of T prime? Then you can graph those, can't you? So how difficult are these problems? Not very? Say not very. Okay. Multiplying by 2, that's easy. Multiplying by 3/4, that's a bit more challenge. Let's find J prime, K prime, L prime, and M prime. All right. Multiplying it times 0, I'm good with that. So that one will stay a 0. That one will stay a 0. All right? Don't be embarrassed to get your calculator out. Let's say I don't know what negative 2 times 3/4 is. Negative 2 times, I can just use 0.75, can't I? Oh, negative 1.5. Who would have ever thought that? So negative 1.5. Well, if negative 2 times 3/4 is negative 1.5, positive 2 times 3/4 better be positive 1.5. What's 4 times 3/4? 4 times 0.75. What am I going to get? 3. So that coordinate's 3. Down here for M prime, that's got to be a negative 3. What's 8 times 3/4? And we've got them all, don't we? Okay? If we're doing one of these, we can do that. If we can find the scale factor by seeing what the coordinates were multiplied by, you can do that instead of the distance formula. I'm okay with it. Okay? All right. Any questions? There's your assignment. Page 508, do 1 through 20, and then 28 through 31. I think you'll find a couple of these to be fairly challenging. Don't skip them. Give them a shot.